If you're studying linear algebra in school, you might have asked the question, what is a matrix? And you've probably been met with the description that a matrix is a grid of numbers. While that's kind of true, it's a description of what a matrix looks like rather than what it actually is and what it actually does. To understand what a matrix actually represents, we need to start with vectors. Take the column vector 3, 2. Geometrically, this is an instruction. Move 3 steps along the x-axis and then 2 steps along the y-axis. But there's a more revealing way to write it. Here, I hat is a unit step in the x direction, and j hat is a unit step in the y direction. We call these basis vectors. These are the building blocks of the coordinate system, and you can get to any point in the coordinate grid through adding together some combination of these basis vectors. However, the coordinate grid isn't fixed. Imagine the coordinate grid is just a stretchy piece of graph paper. We can grab hold of it and move it, bend it, twist it, and tear it. Or you can drag the origin somewhere else entirely, warping the whole sheet. Most ways of doing this are extremely chaotic, and we don't deal with them at A level. Instead, we deal with a subset of these transformations, which are much more well behaved. These are known as linear transformations. Imagine we put a pin through the origin of our stretchy sheet of graph paper. Then we stretched, sheared, or rotated the graph paper as a whole. You'll notice that even though the grid lines get warped and stretched, they stay straight and evenly spaced. In fact, any straight line drawn on the stretchy graph paper remains straight, and since we've put a pin through our origin, it doesn't move. We call this very specific type of transformation a linear transformation, since every straight line remains straight. Since the grid stays straight and evenly spaced, the entire transformation is completely determined by what happens to the basis vectors, I hat and j hat. Once you know where these two vectors land, every other vector follows, because every other vector was just a combination of these two. A matrix is simply a record of where the basis vectors go. Take the following matrix for example. The first column tells us I hat has landed on 2, 0, and the second column tells us that j hat has landed on 1, 3. That's the entire transformation packaged into 4 numbers. The matrix you just saw is an example of a 2 by 2 matrix. It has 2 rows and 2 columns. It reflects the fact that the transformation is from a 2D plane to another 2D plane. However, matrices aren't confined to the plane. They can describe transformations in any number of dimensions. We label a matrix's size as n by m, meaning n rows and m columns. The number of columns tells you how many basis vectors you started with, and the number of rows tells you how many coordinates each one needs after the transformation. A grid of numbers is a surface level explanation of what a matrix is. In reality, they describe the way space shifts as a result of linear transformations.